Good afternoon, and thanks for the convener to give me this opportunity to present our work, and thanks for being here. And this talk will mostly focus on the techniques. There's some background that we have hyperspectral UV instrument. We can measure lots of different species based on their spectral features. And one of the things that degrade the measurement quality is the noise as well as the spectral artifact. And with the current sensor and the future sensor, that actually the signal-noise ratio are increasingly, we have a better instrument with a higher signal-to-noise ratio. And the limiting factor that limit the accuracy of the retrieval quantity are actually now not the noise, but the spectral interference, and which I'll show some example. And we wanted to reduce that, and with that, and there's more information become available from the measurement, then we also have to improve the algorithm or the algorithm physics to achieve better result. So here's obviously we wanted to make the most of the current as well as the future hyperspectral observation. We developed new techniques to achieve more sensitive and more accurate quantification of a trace gas. So our approach have tried to be as general as possible. We wanted to reduce the spectral interference and as well as improve the algorithm physics, and both goes hand in hand. Here's an example of what the spectral interference would look like. The L is the satellite measure the radiance, and the F is the satellite measure the solar irradiance. That's what we have to normalize them to get the before to do the retrieval. Normally, here I have a term called a delta L, which is an addition of the normally straight line, but as well as all kinds of other interference could be represented by this change. And if you do this, you can have a simple approximation, and this would be the satellite measure the radiance in number of photons. And if you normalize them with the solar flux, and you get something like this. And an additional term, a straight line, for instance, if it's only, I assume this is a very simple straight line. They are constant everywhere, so it's equal to 1% of the 310 nanometer, and that would be the spectral signal that would introduce into the measure the spectrum. Now, compared to the normal signal that we measured, here I show a ring spectrum. Normal trace gas absorption would be at 0.01 level. So you can see the simple straight line will introduce a very huge error into the spectrum, and we have to correct them in order to make a very accurate retrieval of the trace gas. And this is a simple case, and with a constant fixed straight line. But in reality, all the instruments that the straight line will be depending on the wavelengths and depending on the scene. So it's very difficult to correct this with the level 1B calibration, and we need to have introduce new algorithm to do this. So, and the new technique I will develop based on, we'll apply it to the Suomi NPP, the OMPS Nadir Mapper. This is a very stable instrument that there's almost no degradation. It has a very high signal-to-noise ratio measurement, but it has significant straight line and other instrument artifacts, as well as ghosting and other artifacts. And all those will introduce spectral interference into the So the new approach and technique we try to develop and try to apply to the Suomi NPP and demonstrate that their effectiveness. So how do we characterize the spectral interference? It's actually very simple. We wanted to make a covariance matrix, the error covariance matrix. It's basically a simple, this is the measured radiance, and we have a modeled based on radius transfer. So that would be, we call, this will be the residual. And you have doing, so you have many observations after you gather the statistic and construct a covariant matrix. And that's how, so this matrix will be constructed for various conditions such as solar zenith angle and viewing angle, as well as the scene reflectivity. So to correct those spectral interference in the retrieval, what we do is that we get the eigenfunction of the covariant matrix, and this is some of the sample that does the first 3 eigenfunction of the arms measurement, and this represent that how the longer wavelengths measurement would impact on the shorter wavelengths. So you can see all these would be basically correlated of any of the spectral measurement that you might have. So if you don't correct them, you will have bias and other artifact in your retrieval product. So our approach is very simple. Just when we do the fitting, we include this as like a trace gas, and removing this, you don't have to. There's many eigenfunction, so you only need to include the first few of them to remove this spectral interference. Oh, here's an example for the SO2, and this is without any correction. That you can see there's a lot of artifact with the, and these artifacts sort of kind of related to the cloud. You can see as you have cloud, you have a stronger line, you have a stronger straight line, and therefore this will be will correlate with any trace gas absorption, and you will have this kind of a spectral interference or artifact in your product. So if I fit a couple of these eigenfunction, so most of those artifacts are being removed, and all the signal becomes appear that even very weak signal that with the volcanic degassing, there's a here and also here, that obviously there's a strong signal from the anthropogenic emission from over China. We can see them all the time. So with this kind of correction, that we can remove most of the artifact in the product and increase the measurement sensitivity drastically. So that's one approach we use to improve that. And next, I'm going to look at how we can improve the algorithms physics to get really sensitive NO2 retrieval from the arms. So this is the normal. This is the high pass NO2 cross section. Normally, that the OMI use the 410 to 460 to do retrieval, and in the arms we only have up to the 380. So the cross section, the differential cross section, is much less than what normally OMI sees, and therefore the overall sensitivity of the measurements depending on the air mass factor or the photon path length, which has a strong dependence of both in terms of the wavelengths, in terms of wavelengths as well as a function of altitude. So combine these two, we will expect that the arms will have much less sensitivity to the tropospheric NO2 compared to OMI. So we'll expect OMI have 4 to 10 times higher than arms. And so to get the signal out of the arms measurement, we developed a new approach, which is direct vertical column fitting. And compared to, here's the equation, I won't go through it. This is representing how the NO2 signal is carried onto the measured spectrum compared to the DOAS method, which is the second term here. This includes all the spectral and vertical variation of the photon path into the equation. So it would have a better representation of how measurement, the measurement spectrum contains the signal. So compared to that, we have obviously more accurate accounting in terms of the spectral and altitude variation of the air mass factor or the measurement sensitivity. But not only that, with the new algorithm, we are able to introduce different strap and trop separation method. And that would allow us to preserve the tropospheric measurement precision and traditional method that separate the strap and trop puts all the noise into the tropospheric column. And also we'll have effective soft calibration scheme, which is adjusting the radiance to reduce the instrument artifact. All this will help us to achieve a better product. And here's an example. Here we show the stratospheric vertical column from the arms. And these are daily measurements for 2 days, and corresponding to that, here we have the tropospheric vertical column. And you can see all the major pollution source, and they are well captured by this. There's no average. This is just simple daily plots. And one thing you can notice is that there's no cross-track striping in this instantaneously plots. Compared to what OMI, you would see that they would need additional destriping. And with our soft calibration, which is done in the radiance level, all those artifacts are removed. We don't have to do destriping anymore. And so compared to OMI, this is monthly average. And you can see on top is the arms, bottom is the OMI. You can see this is for July, which is have a shorter lifetime. You see less NO2. And for December, and you see obviously the pattern is very close match with each other, and you indicating that both arms and OMI sees the same thing. And for a more quantitative comparison, we'll show OMI in red and the arms in blue. And this is at the 30-degree latitude. We just cross from one end to another what the tropospheric vertical column looks like. So that's what this curve shows. And you can see that both of them sees basically the same thing. Obviously, OMI sees the highest tropospheric column than ARMS because it has a smaller pixel size. So in terms of the individual precision, daily measurement, the tropospheric column, actually ARMS has a higher precision than the current OMI data. That doesn't mean that ARMS is a better instrument in terms of measuring NO2. It just says that the new algorithm, new approach, we are able to implement that can do a better job in terms of the retrieval. And I expect that if we apply the same algorithm to OMI, we'll improve the tropospheric vertical precision as well. So, and based on this result, we can certainly say that that we can certainly use ARMS to extend the long-term data record for the OMI measurements. So This is a summary. So we have new techniques that which has enabled us to have unbiased measurement both of the tropospheric NO2 and SO2. We demonstrated with this the ARMS instrument, and this is quite general. It can be used for other instruments as well. So with the end, so I'll show this is a daily snapshot of a pollution event that with ARMS is designed primarily for total ozone measurements, but with the new technique we can make that as useful for air quality application as well.